So we have started a new topics in the last lecture, that is on recovery, recrystallization and grain growth. I have given you some preliminary idea that in metal working we deform the materials to get different shapes, and this deformation will produce different kinds of defects in the microstructure, dislocations, point defects, or even voids or twinning. So once these defects are accumulated in the microstructure, the properties of the materials get affected, mainly the mechanical and physical properties. So because of the accumulation of these defects, the strength of the material keeps on increasing, but ductility and other toughness properties gets reduced, and this is a serious problem in reactive applications. That's why in most of the cases we anneal the material after the plastic deformation, and this leads to what is known as recovery, recrystallization, grain growth depending on the temperature of annealing. So let us have a little bit recap and then we will go into that. So as I said, there are different kinds of metal deforming processes, and each of these processes leads to a huge plastic deformation, and then this can give rise to different kinds of working conditions like hot, cold or warm working depending on temperatures. But especially during the cold working, sufficient amount of strain energy is stored in the material, and this cold working leads to point defects, density, dislocations, twinning, many other things which will increase. And that's why cold working is typically done in ductile metals, because it is easy to deform these materials at lower temperatures. But the issue is that this accumulation of these defects leads to increase in the yield strength, increase in tensile strength, decrease in the elongation and decrease in the ductility as well as toughness. So that's why we heat this material annealed at higher temperatures, and annealing leads to recovery of the or increase of the ductility from very low value to a substantially reasonable value, which can be used for applications. Similarly, strength also decreases. So what actually happens during this annealing treatment? That is what is the basic purpose of discussion on recovery recrystallations. So what I discussed, I'll now simply go back to recovery. Recovery is normally takes place at a lower temperatures. After after cold work we anneal, and it happens at lower temperatures, and it doesn't lead to any apparent change in the microstructures. That means the grain size, the phases, the distribution of the grain sizes, they don't change. Apparently there is no change. So what actually changes? Okay, the thing which gets changed is basically rearrangement of the defect structure in the microstructure. And because of these excess point defects on the line and surface defects, recovery is always associated with this kind of rearrangements of the defects. So point defects normally can get annealed out at the surface or grain boundaries, or even dislocations kind processes. Not only that, other defects like dislocations also gets affected. Let us now discuss one by one of these things. So basically first thing what happens is that the store energy which is there in the material, that's get relieved because of these processes. So external stresses are removed, and but the store energy which is because of the dislocation of things, they gets relieved during recovery recrystallization process, and finally the grains grow in grain growth. So what actually heating does? Heating increases diffusion basically, obviously, because you are providing energy to the system, and this diffusion leads to change of the arrangement of the point defects. They also enhance the dislocation motion. Dislocations can easily move because of these temperature increase, and then dislocation will interact themselves. They can lead to annihilations of dislocations, so the number density will go down, or they can lead to formation of low energy configurations. Both of these three things, that is point defects, movements and dislocation, annihilation and arrangement in low energy configuration, can relieve the internal strain energy. That is the basic purpose, because we want to relieve the strain energy. There are many deformation processes in which after plastic deformation the material is given low temperature annealing treatment just to have a recovery, and this recovery will lead to the arrangements recovery will lead to relief of the internal stress or internal strain energy, and then again the material can be further subsequently deformed. This is done widely in steel industry, that the plastic deformation followed by annealing at low temperature, again plastic deformation, and this cycle actually is repeated several times in the industry. So it is important that what are the micro things happens. So let us now consider edge dislocations. Obviously edge dislocations of different signs will come and they can actually annihilate each other. This is shown there. If this edge dislocation moves close to this one, this position, they will annihilate out. Similarly, if this edge dislocation moves here, this right direction and this one left directions, and they can join. You can clearly see these two planes of the atom. That is what I discussed in the last lecture. This is an extra plane of atoms in the left side, and the extra plane on the right side of myself. So obviously it will be opposite to you. And then once they come closer to each other, these two can join and form a continuous plane. So therefore the dislocation can annihilate out. Not only that, and this can only happen if the both dislocation moving in the same plane. If both dislocations are actually moving on the same glide plane, they can come to each other and then annihilate. But if they are not moving on the same plane, then what will happen? If they are not moving in the same plane, like this one, they are not moving in the same plane, it can lead to void formation. Okay. First it will lead to micro voids, and then it will lead to a bigger void formation. So whatever it is, this relieves the strain energy in the material. That is most important aspect you must realize. So, but what happens to the other dislocations, screw dislocations? One of the best mechanism by which both the edge and screw dislocation can actually relieve the strain energy is by what is known as polygonization. I have discussed this in last class also, again giving you better perspectives. Suppose you have large number of dislocations lying on different glide planes inside the crystals, and the crystal will be obviously bent because of deformations. Now this will lead to huge increase of the strain energy, and this increase of strain energy can create lot of difficulty in getting back the ductility. So what we can do, if you heat it up, dislocations can align along certain directions vertically, and because of that this strain energy can be reduced in the regions which is marked by these blobs. Okay, easily it can be reduced, but by doing and by arranging this way, they actually create what is known as a low angle tilt boundaries if they are all edge dislocations. So these low angle gain boundaries will differ and subsequently create what is known as small angle boundaries will lead to form cells, okay, or basically subgrains. This is actually subgrains. So by that way the strain energy of the majority part of the grains can be reduced extensively. Similarly, if the screw dislocations align vertically along certain directions, so then it will create a twist boundary, and both the tilt and twist boundary will lead to formation of the subgrains. So therefore these three important mechanisms which operate in the recovery stage leads to reduction of the stored energy or strain energy in the material. This is very important for you to realize that this happens sometimes when you do hot working. These kind of situations keeps on happening during deformation itself. Like in case of steel, if it is worked at a temperature of suppose 800 to 1000 degrees Celsius temperatures, deformation and this recovery will happen together, and that is why actually hot working is good, because the strain can be relieved very easily during the process of deformation itself. You do not need to again provide annealing treatments. But during cold working, even in steel also people nowadays do cold working, cold working which is done at a much lower temperature for steel, 300, 400 degrees Celsius, or even room temperature in some cases, depending on the ductility of the steel. So the, the annihilation or the rearrangements of these dislocations and the point defects are only possible when we heat it at an intermediate temperature during annealing stage. So that is the reason we anneal most of the materials after cold working. Now what can happen in the next step? Next step is nothing but, as we increase the temperature of annealing to higher temperatures, higher from the as compared to recovery, we'll have a new kind of phenomenon known as recrystallization. As the term suggests, it's basically crystallization again. So normally crystallization happens from the liquid state, which, as you know, during the solidification course chapter of these courses I have discussed about nucleation of different grains heterogeneously or homogeneously, and that is what is known as crystallization. So nucleation and growth. Recrystallization is what happens in a solid state during annealing of the deformed material. So after recovery, grains can still be strained. Obviously recovery cannot relieve all the strain. The strained regions of the grains can easily be replaced by heating up by the strain-free grains with low density dislocation. Remember, this text are taken from this book by I am just teaching this portion of this lecture from book of A.K. Chena and M.C. Chaturvedi. So you can directly read these books, and these texts are actually taken from that. Now recrystallization is basically nothing but nucleation and growth of the new strain-free grains. Remember, new strain-free grains. It's not only new grains, the grains which will be forming or crystallizing or again growing are strain-free. What is the driving force for that? Obviously, driving force is nothing but strain and stored energy in the material. Difference in the internal energy of the strain and the unstrain, that is what is the driving force. Okay, and growth, as I told you, grain growth is driven by the grain boundary energy. Okay, so therefore this depends on both temperature and time. And let us first discuss the time, temperature. Temperature at which this happens is basically known as the recrystallization temperature. Typically it is between 1/3 to 1/2 of the melting temperature of the material. So it can actually go even up to 0.7, but very rarely. Normally it's between 0.33 to 0.5 Tm. Basically it's more likely 0.4 to 0.5 Tm. A recrystallization temperature normally decreases as a function of cold work. The more the cold work, lower is the recrystallization temperature, because you have more strain energy, and the strain energy is the driving force for recrystallization. So below a critical deformation, recrystallization will never happen. That is why if you deform material by lower amount of cold work, then only recovery happens, recrystallization does not happen, because you do not have driving force left to form new crystals. Now let us discuss two important things. There are two important processes, very important processes, which actually leads to formation of these strain-free grains. First, I have already discussed the nucleation and growth of the strain-free grains, but that is not the only one. Remember, there will be also migration of the grain boundaries, because you have already a strained grain. Inside the grain there are a lot of defects, and during the recovery process these defects have arranged them nicely, so the strain energy can be reduced. But as the new grain forms, there will be migration of these pre-existing grain boundaries which are there. What is that? Well, this can be shown in this way. Suppose we have a strained grain which is more strained, both the grains are strained, one is more dislocations and other one has less dislocation. Okay, this one has less dislocation. Now this is the arrow to which the grain boundary will move from the lower number of dislocations to more number of dislocations. Obviously, because of lower number of dislocation, this is less strain. Okay, this is more strain. The strain energy accumulated is more if you have more number of dislocations. So therefore, the grain boundary which is like this the green color, this will move along the arrow given by the blue. So that is the way grain boundary moves. Why the grain boundary will move along the direction? Obviously the reason is very simple. See, you have a lot of drag on the grain boundary because of the strain energies, and as soon as you know, the cold work is more in this grain, which is more strain energy, so the chances of formation of the strain free grains are more here. Okay, these are very widely happens. So because of this, because of that, the grain boundary movements, the nucleation and the growth of the grains also gets affected. Does not involve nucleation of new grains. The first two means the migrations, and during the migration of the grain boundaries to region of high dislocation density reduces. Okay, grain boundary can actually accommodate more dislocation. That's why, as the grain boundary moves from low deformed regions to high deformed regions, the dislocation density will reduce in the high deformed regions, because this dislocation will be then part of the grain boundary, because grain boundary can absorb the defects. Grain boundary is region of defective region, so therefore these dislocation can then actually they can actually be part of the grain boundary. So that's why actually grain boundary moves and reduces the strain energy. So this is another way of reducing the strain energy. Okay, so now question is the temperature. As you have seen, we do normally three types of metal working: hot working, cold working, and warm working. And we normally define, I told you, that hot working happens above the recrystallization temperature, cold working is below recrystallization temperature, warm working is between that, 0.3 to 0.5. That's what is given here. Now recrystallization temperature is somewhat close to 0.5. Normally it is more than 0.5 or close to 0.5, but as I said, it can be between 0.4 to 0.5 also. So that is the temperature of recrystallization, and this is true always. So that means it scales with the melting temperature. For pure metal alloy, it scales with the melting temperature. That's what you should remember, and this is understandable. Well, it will be clear to you very soon. This is a plot of recrystallization temperature versus cold work, and this is again taken from Callister's book on materials and engineering. As you see here, recrystallization temperature strongly depends on the cold work. It also depends on strain rate. Let me tell you, and also mode of deformation. If you are deforming by torsion or by normal uniaxial loading, things will change. But obviously, percentage cold work does affect the recrystallization temperature strongly. As you see here, you have a critical deformation required, and remember this is for steel. So in order to have a recrystallization, you need about 5% strain. Below that, there will be no recrystallization. And as you increase the plastic work from 5 to about 30%, the temperature can go down from 900 to about 500 Celsius temperature. So that's what we said, it varies from 1/3 to 1/2 of the melting temperature, depending on the percentage cold work. And after that, the recrystallization temperature doesn't change much. Okay, this is for a particular steel. So there are a lot of steel which can recrystallize the temperature of 500 to 550 Celsius temperature. And so obviously, once a huge amount of strain is built up in the material, that itself acts as a driving force for the recrystallization. So therefore, the recrystallization temperature becomes independent of the cold work beyond certain values of the cold work. Second important thing is that recrystallization, as I told you, is the driving force is basically free energy difference between the deformed and undeformed crystal material, and this is given by delta H minus delta T delta S obviously. Now delta H is what? This is stored energy due to deformation. That's always can be defined as a minus ES, and this value has been found to be much higher than the T delta S. So therefore, we can actually ignore the T delta S part, and we can actually write down delta G is almost equal to ES. And to give you a value which is given in this book, the value of ES basically, so for I think it's for what material? Yes, value of ES for the silver gold alloy, silver 70% gold and 38% silver, it's about 0.33 kilojoule per gram atom. Okay. So that's the value available. So now this is the important aspect. So ES actually depends on, it depends on percentage cold work, it depends on the deformation process, strain rate, and also the temperature at which deformation is done. So you understand that the ES is the critical parameter, and remember ES, it doesn't depend on temperature. Okay, ES actually depends. What I mean by dependent is it's a weak function of temperature. Okay, normally it's independent of temperature. So because it's a stored energy, so that mostly depends on the percentage cold work, strain rate, deformation processor. Let me also tell you a few important facts. Okay, about the recrystallized temperature. Obviously, as I told you, as higher the temperature metal working, and lower the strain energy stored, obviously, because recovery will happen subsequently as strain energy will be relieved, and this will lead to higher recrystallization temperature. Second important aspect, the rate of recrystallization. Rate of recrystallization is given by this formula. As you have seen, n dot is given by n nu exponential, that this is all exponential function, minus 16 pi, okay, this is pi, and q, pi gamma q, sorry, this is gamma is the surface energy, or interfacial energy rather. So, sorry, interfacial energy is, this is V square, not E square. V, capital V is the volume divided by 3 ES square plus delta Gi divided by KT. Let me define all these terms. I have already defined your ES. V is the volume, okay, obviously the atomic volume, okay, atom volume per atom. ES is the stored energy, and nu is the frequency, n is the number of atoms presence, and gamma is the surface energy, K is the Boltzmann constant, T is the temperature, and what is delta Gi? Delta Gi is the activation energy for the grain boundary diffusion. Okay. Why it comes into picture? Because grain boundary moves during this process, that's why. So that's why, and this is an plus term. Remember, grain boundary migration requires energy, and this energy is positive term. So therefore, higher is the grain boundary energy, grain boundary diffusion energy, lower will be the available energy for the systems, and it's there. Now, as you know, normally ES, predominantly ES is independent of temperature. It's not always the case, but most of the cases. And because ES independent temperature, n dot, the nucleation rate, is also independent of temperature. It's not dependent on temperature. Okay, so but it depends on time. Why it depends on time? Well, let me explain that. But so that means ES, as that means the n dot is basically is not only a function of temperature here. You see here temperature is there, okay, KT, but it also a function of time. And we'll see later on, maybe in the next subsequent lectures, once you know the growth, we can actually define these whole kinetics using Johnson-May-Labrami type of equations. And that's a classical way of representing the nucleation and the grain growth during recrystallization and again process. So question is this picture I always show you again and again, because this particular slide is for you very important to keep it in your mind always. As you know, this is the picture. As you see here, let us look at the bottom picture, which tells you the things more easily. What do you see here? You see here that at a temperature, handling temperature versus grain size, and this is this microstructure given schematically. So at lower temperatures, you have cold work grains, lot of dislocations and point defects and other defects are present. And then as the lower temperature handling leads to recovery of these defects, so defects means dislocations mostly, or point defects, they can get annealed out at the grain boundaries, or dislocations can also anneal out, or they can actually form voids, or they can actually arrange by polygonizations. And then higher temperatures, what you basically leads is basically nucleation of the stain-free grain, so what is known as recrystallization process starting. And then if you increase the temperature further beyond 0.8, the grain starts growing, because that's the way they can again reduce their grain boundary energies. And this whole process drastically affects the mechanical properties. Ductility improves subsequently. See, ductility improvement is not very large during recovery stage, but at a later stage when recovery and recrystallization happens together, the ductility improves substantially. So one can actually stop here, okay, at this temperature, because you have a critical value of both strength and ductility. Strength is about 470 and ductility is about, something like about 40% can be achieved. And any subsequent increase of temperature leads to drop of the tensile strength further, and ductility increases, but ductility doesn't increase much. Much means substantial increase happens only during the recrystallization process. That's why the strains can be relieved extensively. So at the higher temperature, when the grain grows much, obviously the strength decreases very, very heavily. As the grain becomes bigger, the Hall page mechanism starts operating, and the grain size increase will lead to decreases in the tensile strength substantially. Similarly, the ductility will improve. So, but this is at the cost of huge decrease in the strength. So therefore, in actual industrial practices, the temperature of annealing temperature should be chosen properly rather I would say, in order to have a right combination of the strength and ductility during these deformation and annealing processes subsequently. So that is the most important message I like to tell you. In the next lecture, we are going to discuss about some of the aspects of recrystallizations which are remained, and then grain growth, and finally we will talk about Johnson-Labrami types of kinetics of the recrystallization process.